Hey guys, we are going to start chapter 2 today, which is the beginning of our investigation into the derivative. So the derivative is going to be a topic of discussion for quite some time. So it's really important that you take your time and listen to the lesson today very closely so that you can establish a strong foundation. Before we begin in the calculus part of the lesson, let's review what a tangent line means. So this may or may not have been something you touched on in geometry, but a tangent line is a straight line that touches a curve at only one point, not crossing through the curve, just touching the curve at that point. So the one on the left is an example of a tangent line. Notice it's not crossing through the curve itself. The one on the right is an example of something that's not a tangent line. In fact, that actually does have a special name. This one is called a secant line. So a secant line is a function or a straight line that crosses through the graph at 2 points. So we're just going to start with drawing some tangent lines on this curve. So make sure that when you draw it, you're making sure that it is a straight line and it's not crossing through your function. So it just kind of hugs the curve. And you'll notice that as I draw these tangent lines, that they all seem to kind of follow the curve, meaning like when the curve starts to go down, the tangent line also goes down. When the curve starts to go back up, the tangent line also goes up. So the tangent line is very useful in helping us find characteristics about a curve. All right, so here is our first question. And when you look at this graph, you will notice that there's a tangent line drawn, this darker blue line. You'll notice this tangent line is drawn, and it is going through the point 1, 1. But it's really kind of hard to tell, but there actually is another line right here, this guy. This is another line that's drawn that goes through this point of tangency, but also goes through another point. Because this goes through 2 points that exist on the curve, this is called a secant line. So here's the issue. The issue is I want to know what the slope of this tangent line is. But in order to find slope, remember that you have to know 2 points because slope is y minus y over x minus x. I do not know anything about any other points on this tangent line other than the point 1, 1. I do, however, know that there are 2 points on the secant line, this lighter blue line. I know that there's 2 points on that line. One is 1, 1 and the other is x squared. So I could find the slope of that secant line. And that's exactly what we're going to do first. We're going to say, well, you know what? The tangent line and the secant line are pretty similar. They're almost the same. So if I can find the slope on this secant line, then that would actually get me like an estimation of the tangent line's slope. So I'm going to write it like this. M is slope, and I'm going to write tan underneath to mean like the slope of the tangent line. We're going to say the slope of the tangent line is similar to the slope of the secant line. And the slope of the secant line, I could do y minus y over x minus x to find that. Except I'm going to be more specific, and I'm going to say that my y values are actually x squared, because that's the location of this black dot, and 1. So I'm going to say x squared minus 1 over the x value minus the x value, so x minus 1. So that would be a more detailed way of writing the slope of the secant line. Now, we could do better, okay? We can actually get a very accurate representation of our tangent line if we do this. Let's use limits, okay? So this dot right here is on the secant line. We just spent a whole chapter studying limits, and we know that limits are used when you want to approach something else, right? You want to study what the function does as you get closer to some specific location. That's what we're going to do right here. We're going to take this point And we're going to say, well, you know what? If I were to move this point super, super close to this point of tangency, then my line would shift and almost resemble the tangent line. So I want to take this dot, I want to slide it down and get really, really close to this other location. And that should give me an even better estimation of the slope of the tangent line. So the way that we'll do this is we'll say the slope of the tangent line is, we said, similar to the secant line, but if we take the limit as x goes to 1, then we're going to get a better estimation of what the slope of the tangent line is. And by the way, I said as x goes to 1 because I want this point to slide down, but really what's happening is the x coordinate is getting closer to this x coordinate, which is 1. So this is a very, very accurate way of measuring slope when you are looking at a point of tangency. And the good news is once you get this set up, you know what to do because we just spent a whole chapter studying limits. So now we're just going to kind of go through and handle this with some of our limit techniques, which in this case, I'm going to be factoring and canceling. So I would have the top would factor down, and then the first binomial will cancel with the denominator, and that's going to give me the limit as x approaches 1 of x plus 1. And that's something we can just do plug and chug now, and so we would get 2. And remember, 2 is representing the slope of that tangent line, okay? Now, there's another step because it does say in the directions that they are looking for an equation of the tangent line. So to do that, we're going to rely on using our equation from our point slope equation, which is only useful when you have straight lines, which we do here for the point of, or for the tangent line. So we are going to apply this using the point 1, 1 as your x1 and your y1 values. So by minus 1 equals 2 times x minus 1. And we could continue by solving this equation for y to write it in slope-intercept form if you want. It's not required in the directions, but sometimes in your book you may have to do it that way. Okay. So it says, this is just a slide kind of giving you a more, like another look at tangent lines and how they should be drawn and what they were used for. We've already discussed that. So let me just show you a quick demo for the tangent line situation. So here I have a secant line, right? And I want you to watch what happens when this secant line turns into a tangent line. So right now, the tangent line should look like that. My secant line is nowhere near where the tangent line is because these 2 points are really far apart. But the closer I get to moving this green dot over to the purple one, look how close those tangent lines those lines become. You almost can't even tell the difference between them when you zoom in. So the closer the green dot gets to the purple dot, the better the estimation becomes. Okay, here we go. So we're going to now take this concept and we're going to turn it into a formal definition. And we're going to do it 2 different ways. Okay, so I'm going to ask you to draw this little curve with me, and we're going to kind of use this little curve to help us set up this formal definition. Okay, so let's say we have a point like right here, and we're going to call this point A. And if this is the x coordinate, if it's called A, then the y coordinate at that location would be f of A. Okay, let's have another point up here, and we're going to call this other point x. And if this down here is x, then this y value would be called f of x. And the idea is we're pretending we have a straight line, a tangent line, So let me get a line going through point A. So we've got a tangent line going through point A. And what I want to do is find the slope of this tangent line. But in order to do that, I would have to start with finding the slope of the secant line. And I have to do that because I have to have 2 points to find the slope of any line. So I'm going to start with using this red dot as my second location. And the whole time I'm doing this, I'm going to try to move that red dot closer to the blue one to get a more accurate estimation of the slope at that point of tangency. So this red dot is moving closer to point A. So here's how the definition is stated. It says the slope, and when they say m, they mean the slope of the tangent line, is equal to the limit as x approaches A. So that means that as the red dot gets closer to the blue dot. And then this formula here, f of x minus f of A, well, that's just the y values at these points. And then x minus A is just the x values at those points. So really, this is just basically saying y minus y over x minus x. Okay, so this is what we just demonstrated in that first example, is that if you want to find the slope of your tangent line, you're going to take the slope of the secant line and kind of slide this red, the second point, closer to your point of tangency. So really, f of x minus f of A, that just means y minus y. And then down here, this means x minus x. So that's just another way of writing slope. We could look at this in a different format. So this one's going to look a little confusing at the moment, but let's draw a picture to match. So I have another point A, and I have the y value would be f of A. All right, this time I'm going to call this second point, I'm going to call this A plus H. And when I say H, what I mean is H is like the width or the space between these 2 points. Okay, we're calling the space between these 2 points H. So if this location, this x value is called A plus H, then the y value would be f of A plus H. Okay, now the limit definition is still going to have kind of a fraction set up. And you'll see on the top you have f of A plus H minus f of A. Well, that's just the y value minus the y value. So everything seems kosher there. The denominator, though, only has an h. Here's why. We know that this is supposed to be like slope, which means y minus y over x minus x. Well, when you do y minus y, you get the top. When you do x minus x, you get A plus H minus A. Well, A minus A cancels and leaves you with just H. So that's why you're just seeing an H here. The limit is also slightly different because it says let's take the limit as H approaches 0. Well, the limit as H approaches 0 means that the gap between these 2 points is closing. So really you're just moving this red dot over closer to the blue dot. So it means the exact same thing as your previous limit definition. All right, let's look at an example with a function. So we have a point of tangency at 3, 1. Find the slope of the tangent line. And I think we have 2 different definitions that you can use whenever you feel like. I think I'm going to go with the x approaches A situation. So in this case, the limit is going to be as x approaches 3, and that's because the x value that we are looking at, the point of tangency, is 3. So I'm going to say as x approaches 3, and then I'm just going to write down my limit definition. So f of x minus f of A over x minus A. Okay, so remember, your A value is 3. So I'm going to go through and plug in 3 everywhere that I see an A. Then this would be like f of 3 up here. Now I need to figure out what to write for f of x. Well, look at your problem a little closer. because f of x is given right up here. So f of x is 3 over x. What about f of 3? F of 3 just means what is the y value when x is 3? The y value when x is 3 is 1. So I need this to be 1. Now I have it set up in a way that I can continue with solving. So I'm going to use all my limit tricks to get through this problem. And I can't plug and chug. I can't actually factor and cancel. But one rule that's not really written in the list is get a common denominator. So that's what I'm going to do. Is up here I'm going to get a common denominator. And basically my end goal here is just to try to make it look algebraically different and hope that maybe something will cancel or factor or something like that. So I have 3 minus x on top over x. And then all of that is over x minus 3, which then I can do outer, inner. Outer, inner. And let's see, I would have 3 minus x over x times x minus 3. And 3 minus x on the top can be flipped if you take out a negative. So I'm going to make that negative and then put x minus 3. And I want to do that, that way it'll cancel. Cancel that. So then we can apply the limit. So all I have left is a negative 1 over x. And I'm going to plug and chug and get negative 1/3. So that is my slope of my tangent line. Okay, now I need to find the equation of the line. The line goes through the point 3, 1. So I'm going to plug that into my point slope equation. And I'm going to go ahead and distribute, I think, and just kind of solve it all the way down. So this would be negative 1/3 x plus 1. Add another 1, and we get negative 1/3 x plus 2. Okay. So what we're doing here is we are kind of trying to figure out how science and math kind of meet up. In the form of velocity. So that's our first topic of discussion with this. So you guys know that slope is equal to rate of change. Okay, slope is equal to rate of change. And rate of change is equal to velocity. This rate of change means like your change, it could mean your change in distance over time, and distance over time is, an example would be like miles per hour or something like that. So rate of change is equal to velocity. So let me give you 2 definitions for velocity here. There is one listed on your paper on this slide, and it is called average velocity. Come on, there we go. Average velocity is equal to your change in position, which is called s, over your change in time. Okay, so change in position means like how far did you travel distance-wise and how much time has passed. That is kind of like finding slope. Your instantaneous velocity is like the velocity at one moment in time. So our average velocity would be like the speed over an interval of time. Instantaneous velocity is equal to what is the rate of change at this single moment. So this is going to be equal to using the limit just as you have done. So I'm just going to put the limit definition. So exactly like finding the slope of a tangent line. That's the same thing as asking for instantaneous velocity. And so here's one of your 2 different ways, different definitions that you could use to find that. There it is listed again. All right, so here is a question that we're going to answer together. I am going to start by going over here and saying that the function is equal to 4.9 t squared. That's the purpose of this whole, section here. Okay, so it says suppose that a ball is dropped from the upper observation deck of the CN Tower 450 meters above the ground. What is the velocity of the ball after 5 seconds? So to do this, I am going to need to find the velocity, but I feel like the way that it's worded, it is implying that they want us to find the instantaneous velocity. Okay, so to do that, we have to take the limit, and we're going to use that second definition called the limit as h approaches 0. I'm just going to write the formula down here. Now, in this situation, we would be taking the limit as h approaches 0, and our a value here is like what you're approaching. So in this case, that is 5. So we're going to change this to the limit as h approaches 0 for f of 5 plus h minus f of 5 over h. Okay, you don't have a graph to look off of like last time. However, you already know how to do this. Just pause and think for a second. How do I find f of 5? Or how do I find f of 5 plus h? Easy, guys. This number in the parentheses represents x. And it means take this, whatever this thing is, and plug it into your function for your input value. In this case, our input value is a t instead of an x, but so what? That's fine. So we're going to take each of these values and plug them into the function in place of t. So that would be 4.9 times, for the first one, 5 plus h squared. Oopsie. And then 4.9 plugged into the function again would be, or 5, I'm sorry, plugged in. 4.9 times 5 squared. Now I really do want to take the limit, I just cannot right now because it is, if you plugged in 0, you would get something that's not computable. So instead, we're going to go through and multiply everything out. So I would get 25 plus 10h plus h squared minus 4.9 times 25. If you wanted to, you could distribute at this point. I actually do not need to distribute because I do see that all my terms are multiplied by 4.9. I think I'm going to stop and I'm going to write this in a little bit of a different manner rather than multiplying by 4.9 all the way through. So I can group everything together and put the 4.9 on the outside. And then when I do that, things start to cancel. So 25 minus 25 is nothing. Take that out. I'm also going to do one more step. I'm going to take out an h from each of the terms I have left. So on the outside, it will be 4.9h, and then 10 plus h in parentheses. Now I took out the h because I knew that it would cancel with the h in the denominator and give me a little bit more room. And now I can do the last step, which is to plug and chug. So I would get 4.9 times 10 plus 0, which is equal to 4.9 times 10, or 49. That represents your instantaneous velocity. And remember, velocity is like a speed. So this one, if you look back at the units given in the problem, this would be meters per second. Okay. The last thing we have to discuss is just a new vocabulary word that is not going to go away anytime soon. This new word is called a derivative. And so a derivative is actually something that you have just done with me. You are finding the slope of the tangent line. That is what a derivative represents. So you could also say a derivative represents the velocity of an object at a certain point. We need to know how to do this because anytime you calculate a rate of change, whether that be in engineering, chemistry, economics, nursing, science, any of the sciences, then it's helpful to kind of have that common term to represent what you're doing. So you're taking derivatives a lot for real world situations. And so a derivative is, I want you to get used to the notation first. It's F with like an apostrophe sign and then some kind of number or letter in parentheses. You would read this as F prime of A. F prime of A is how you read this. Okay? And when I say, find the derivative of the function at 2, I mean to do the limit definition just like we've been doing for the last few examples. So let's look at one of those. And that will probably be it for the day. So in this example, it says, find the derivative of the function f of x equals x squared minus 8x plus 9 at the number a. So since I'm not given an actual value for a, I think it would probably be easiest to use the limit definition where you say like that h is approaching 0. And I'm going to write the whole formula out first so you just have that again here in front of you. Okay, so the goal is to find f prime of a, which means to find the slope of the tangent line. So remember that you're going to start this problem by plugging in something in place of f of a plus h and in place of f of a. That just means take an a and plug it in everywhere that you see an x into your function. Same thing goes for the a plus h. Take a plus h and plug it in everywhere that you see an x. So I'm going to write this all out. I'm going to start with a plus h. Plugging that in would look like a plus h squared minus 8 times a plus h plus 9. And then subtract f of a. And f of a would be this equation with a's in place of the x's. Okay, and then that whole thing is supposed to be over h. Your next move would be to try to take the limit now, except you're going to get stuck because you can't plug it in the denominator. So you're going to have to start working through the algebra, squaring things, distributing things, etc., to get it to be, something a little different than what you currently have. And if you do this right, you're going to have a bunch of terms cancel. Oops. There we go. All right, so what cancels here? A squareds, those go away. 8a's go away. 9's go away. Now, look a little closer. And notice that each of the terms you have remaining do have a letter h in them. So we are going to factor out an h from all the remaining terms. Remember, I wanted this to happen because I wanted these h's to cancel so that I can actually solve the darn thing. So, last step. Take the limit as h approaches 0 for 2a plus h minus 8. Remember, the limit is as h approaches 0. So now when you go to do your plug and chug, you are plugging 0 in place of h, and you're going to end up with 2a minus 8. And remember that that is equal to your derivative, which is called f prime of a. Real quick, let me explain what this formula even means. This just means that now I have an equation that will tell me the slope of my tangent line at any point on that curve. So if I am at the point, 3, I could plug 3 in place of a and find my slope, and that would give me -2. Or I could plug in 400. What's the slope when x is 400? Plug 400 in and solve, and you find your slope there. So this is just an equation that finds it, makes it a little faster to find the slope at a certain point, because now you have something you can plug in to solve very easily. Okay, I think this one is very similar to example 1. So I'm going to let you try that on your own, and then the answers will be posted in the notes that I attach on Classroom.